Hi. Um, I want to go through a lesson today with Engineering Tomorrow about decarbonization and how green hydrogen can play a role in this. So the goal today is to kind of to show you how engineers can be or play a part in the decarbonization of the world's economy and why it's so important that we do this. So first of all, let's talk about what is decarbonization. So decarbonization is essentially the reduction or elimination of CO2, carbon dioxide, or any other gas that acts like CO2 in the atmosphere. If that comes from, typically it comes from manufacturing or from the production of energy. Sometimes these other gases are called greenhouse gases. Actually, they're all called greenhouse gases, GHG, because they contribute to the Earth behaving more and more like a greenhouse, where the sun's rays get trapped, and over time, the temperatures start to rise. And what we're seeing is a change in our climate. And climate change is causing a lot of problems. So, why do we want to decarbonize? This plot here shows you a little bit about over the last 400,000 years, so a long, long time, what the carbon dioxide concentration in the atmosphere has been. You can see that there's definitely cycles that last tens of thousands of years at least. And these cycles are what they like to call climate cycles. But if you look at where we are today, we seem to be off of the normal cycle. So now if I zoom in on that zero, so just look at the last two, 300 years, this is another graph that the red or pink line is the y-axis for that is on the left, and that's the CO2. So that's a zooming in of the whole data set that we used, so that we had on the left side of the page. On the right side of this graph is the CO2 emissions from mankind, from our economies, and you can see that really starting in around 1900 or late 1800s, we started to see a real change in the emissions. And most people would argue that these are connected impacts. CO2 impact is coming from increased emissions. And most people would argue that these CO2 emissions are causing climate change, and are at least having a big impact on climate change, which is causing more severe weather. So this is why we have to do it. So where are these greenhouse gases coming from? This chart is a Pareto chart. It's a bar chart, but it's also called a Pareto chart. Pareto chart typically shows you biggest factors or biggest drivers of an event in different categories. And here we're plotting the categories of country in terms of their emission of CO2 or carbon dioxide equivalents. So it's essentially greenhouse gases. A couple of things I want to show you here. First of all, China is the biggest driver. And that's not surprising. China, over the last several decades, has had a huge growth in their economy. A lot more middle class people who can afford to buy cars and fancy and take airplanes and go on vacations. They want to have houses. These houses need, heat. They need electricity. So they've had a huge boom in their economy, and it turns out that a lot of their electricity that's produced in China comes from coal. So again, that's just driving more and more emissions. So that's not a surprise that China is number one, at least in this list. Now, a couple of other things, just terminology that I want to mention. These greenhouse gas emissions, the CO2 equivalents, where they're including things that's called LULUCF, or land use change, and forestry, which is essentially, it includes the impact of cutting down forests, which are actually sinks of CO2. So if you cut down trees, then there is less biomass that can absorb CO2. So that has a net increase impact. The other thing I want to mention is these Kyoto gases, which is the table. CO2 is the most common gas that we talk about, but other gases that get released have equivalent or more severe impact on the greenhouse phenomenon. So, for example, when methane is released, it has the equivalent of 25 times the impact of carbon dioxide. So, if a pound of methane is released, it's like releasing 25 pounds of CO2. If a pound of nitrous oxide is released, it's almost 300 pounds of CO2 equivalent. So these are important factors that we'll talk about a little bit. So we talked about where the countries that are emitting. Now, what industries are actually, or what are the sources of all these CO2 or greenhouse gases? And this is a pie chart, which gives you an idea of the breakdown of all the CO2 or greenhouse gas that is emitted. What are the various industries? Where are they coming from? So first of all, you can see it. Electricity and transportation have a big driver because electricity, a lot of it is traditionally been coal or fossil based. Transportation, as you know, gasoline, diesel, airplane fuel, or aviation fuel. And these are all fossil based. So when they are burned, they're releasing CO2. I want to mention agriculture and land use and landfills. This is another driver. So crops actually, if there's poor crop management, that can lead to not so much CO2 use, but actually nitrous oxide release if you're overwatering or over-fertilizing. Livestock, you may have heard about how cows, they belch gases, which come from a process called enteric fermentation in their stomachs. And this is actually another driver of greenhouse gas emissions. And then finally, landfills. When you bury food waste in a landfill, it will start to digest. It'll start to convert, and it converts into things like methane, which gets released. So these are all drivers. Now, we'll talk a little bit more about the industry pie, the slice of the pie, a lot more. But the question is, what can we do about this? So you may have done some of our vehicle labs, and you'll see electric vehicles that's getting at the transport issue. So using electricity, green electricity, to fuel or to power transportation is one way of helping this. You may have done a renewable energy lab, wind and solar, and that is literally the definition of green electricity. That is more and more displacing coal and oil and other fossil fuels. So that's a positive impact on reducing emissions. Now the thing is, in industry, there's no one thing no simple solution, no one thing that can solve the problem. So we're going to talk a little about this more in the next page, but this is kind of the first step in trying to figure out how do we decarbonize the global economy, and as a result, hopefully turn around this impact of climate change so we can get back to a more stable situation. All of this activity that's around reducing emissions is part of what we call the energy transition. The energy transition is a major area of focus of engineers, and it's a major area of focus of investment around the world to try to transition to a much more or much lower carbon intense industry. So let's talk more about these industrial emissions. So there's a number of things that's on the page. You can read through them. I'm not going to talk about them all. But there's a lot of places where you're releasing more methane than necessary. You're using fossil fuels to heat large and high temperature furnace operations for, say, iron, steel, and also kilns for cement making. But one of the things that hits a lot of these areas is actually the use of hydrogen. Hydrogen is obviously a great chemical. It's a great gas, and it's used to reduce reactions, and it does show up in a lot of different areas. So it shows up in cracking of petroleum fuels, in the production of ammonia and methanol, and it can also be used as a fuel source. It also is used, and quite often is used to produce what we might call sustainable fuels. So things like sustainable aviation fuel, SAF, will require hydrogen. Now, hydrogen is a great thing, but the problem with hydrogen is that traditional ways of making hydrogen generates a lot of CO2. So if you could find a more green or non-traditional way of making hydrogen that doesn't generate CO2, that could have a positive impact. And that's what you're going to do today in your lab. So how is hydrogen produced today? Today, it's done mostly by something called steam methane reforming. You can see it up in the upper left page here. Essentially, what you have is you're reacting methane or natural gas with steam. And the output of this is hydrogen and CO2. If you look on the page, there's the chemistry of the process is shown there. And in the end, what you have is that for every pound of hydrogen you produce, you actually produce theoretically 22 pounds of CO2. Now, this is the traditional way of making hydrogen. And what they do is they call this way, this is the hydrogen they make in this way, it's called gray hydrogen. Now, if you capture the CO2, you'll actually be able to convert that hydrogen to a different name called blue hydrogen, because now you're converting the natural gas into hydrogen and CO2, but you're capturing that CO2. So the CO2 is then not released to the atmosphere. But there is an alternative. There is another way of making hydrogen from one of the most abundant materials we have on Earth, which is water. Water is just H2O. It has the hydrogen in the element or in the material. And the way this is done is through a process called electrolysis. And hydrogen produced by electrolysis that does not produce CO2 is called green hydrogen. So electrolysis is basically a process where you take electricity and you run it through water. And the water, if you can create this current, the electricity came from renewable energy, you break down the water to form hydrogen at the cathode, the negative side, and oxygen at the anode, the positive side. This is the very basic electrolysis cell. Now, this is an opportunity to create green hydrogen, which would reduce a significant amount of CO2 going into the atmosphere traditionally. If there ever was a place where engineers were, had a big impact, it is the process where we take this standard electrolysis process and turn it into this, which is a full-scale green hydrogen plant for producing green hydrogen from water and electricity. Now, the nice thing about this is that for every pound of hydrogen you produce, you don't produce any CO2. So this is what green hydrogen looks like. So the concept is that if you could take renewable energy and you from wind, solar, geothermal, any source, you could use part of that through the electric grid to charge your electric vehicle. You could use other parts of it, that electric grid, to run heat pumps to heat your house. And of course, in the summer, if it's hot, that electricity can run your air conditioner too. And then part of that electricity that's green can go into an electrolysis process where, together with water, you produce green hydrogen. And the concept is that the chemical industry then could use that to produce fertilizers and methanol and things like that. The other chemical industries can synthesize fuels like sustainable aviation fuel and fuels that can be used on land and sea, as well as other things. But there is one big question mark around this whole thing, and that is, this is not going to happen if it's not economical. You have to do this in a way, and this is where engineers have to understand the economics of things as well as the physical properties and the physical conversion of chemistry in chemistry. It has to be an economical process. So, and it isn't always, but through various improvements in technology, potentially incentives with government, that can maybe help make this economical. So what are you going to do today? You're going to build an electrolysis cell and you're going to make some green hydrogen. So it's very straightforward, actually. Now on the left, you can see the diagram of what this is going to look like. You're going to have two pencils that are going to be your electrodes. You're going to basically sharpen both ends, and you're going to put them in water with a battery, hook up a battery, and you're going to start to see the bubbles forming. And what we want you to do is to capture this green hydrogen. Remember, the hydrogen is coming from the negative electrode. So you have to figure out how is this going to look. Now, the picture on the right is a cell that I made. It's not the best cell. Zoom in. Well, first of all, these are the reactions that you're going to see. You're going to see the conversion of water to hydrogen and to oxygen. We go to the next page. What another option is you're going to be able to do is take and add some salt to that water solution. And in that case, you're going to change the chemistry a little bit. You're going to then produce hydrogen and chlorine. And it'll be interesting for you to see how that is different. You can do some studies on developing that. But most importantly, you have to design a way of capturing these gases. So this is what my design looked like. What I have is a clear plastic straw, put it in half, and then I folded it over. And it's very important that you fold this and glue the inside of the straw because it has to be fully sealed on the end. What you're going to do is you're going to start by filling the straw with water. Hold with your finger the open end, tip it over, and put it in your little pond of water there, which is in the plastic bottle that you've cut apart. And that water level, as long as you've sealed that straw well, that water level will stay there. If it starts to drop without you doing anything, that means that there's air leaking in the top. So make sure that is sealed and doesn't change. You might want to actually keep it in the water for a few hours to make sure it's not leaking. Then what you're going to do is you're going to hook up your cell and you're going to figure out how do you capture as much hydrogen from your negative terminal as you can. And what I did was I just took a little slot in the straw and I put my end of my pencil in it. But you can do better. I'm sure you can do better. And once you get that hooked up, after a day or so, maybe even longer, I want you to see the gas, the water level going down. And here you can see it. You should see the gas filling up the top of the straw, the green hydrogen, and the water level being pushed down. And the basic question is, can you measure your hydrogen generation rate? I'd be very curious if you could. And you can do that. You need to know the cross-section of your straw. And then if you know how fast it's moving down, you can calculate a volume of generation, say per hour or per day, whatever. So how can you calculate cubic centimeters per hour or cubic centimeters per day? That would be a great outcome if you can. So let me go back to this first of all. You're going to build a little electrochemical cell to produce green hydrogen, but back to this scaled up version of this. To build this is going to take people with skills to build and operate a plant like this. So it's going to take engineers, obviously, because we're engineering tomorrow. We're talking and trying to get you introduced to what an engineering career looks like. But when we talk about that, we talk typically about 4-year college degrees. But it's going to take more than just engineers to build this. It's going to take people who can, it's going to take people that are mechanics, pipe fitters, plumbers, electricians, I&Es or instrumentation electronics. You have to have people who know how to control and write control algorithms to run the valves and everything in this. It's going to take welders. It's going to take all kinds of people with tradecraft. It's going to take people who understand the process and who can work in the control room to operate the plant, understand how to keep things safe and keep the people safe. It's going to take chemists and lab technicians who can work in the labs, because there's going to be labs in these types of places, as well as many other things. So a lot of these skills are going to be things that you can learn not only in 4-year colleges. If you're not interested in 4-year college, you can learn these skills in 2-year colleges, tech schools, trade schools, apprenticeships. There's all kinds of opportunities. And this is just one example of the energy transition. these skills are going to be required across the board in all areas of the energy transition. So although we do encourage students to look into engineering, there are different ways of being engineers in the world today. And honestly, there's a shortage of really good people who know how to work with their hands, how to build stuff, how to basically fix things. So think about that as you're making your decision on a career. So a couple of questions at the end just to finish up. Can you design a reactor that captures all the hydrogen? Why doesn't the water in the straw drain out when it's just sitting there without hydrogen or gas going into it? And then there's some other questions. So I hope you enjoy this and think about. Hope you have a better understanding of decarbonization, what the energy transition looks like, and how you may be able to make a difference.